For the first part of our experiment, again, we're measuring regularly shaped objects. So I'm going to show you an example of measuring a rectangle. Well, a rectangular solid. And you have to measure 3 dimensions on that. So here I have a centimeter ruler. You can get these anywhere. And I'm going to line up one end, the 0 end, with the end of my box. And be careful about keeping the ruler straight. And I'm going to find out where it lines up. So to me, it looks like about 15.71. I'm looking for 2 decimal places. So again, to talk about the ruler, you can see here there's a line for the halfway mark between 15 and 16, and then we have lines indicating 1 millimeter at a time. So I want you to estimate to the 10th place. So you can see that the edge of the box goes 2 lines past the halfway point. So it looks like about, it's more than 15.5, slightly more than 15.7, so we're going to call it 15.71 for that dimension. So I would take a paper and write that down. We're going to do length, width, and height. So for length, 15.71 centimeters. I'll be looking for 2 decimal places on all of your measurements, whether you're doing a rectangular solid or whether you're doing a cylindrical solid. So we need to do width and height next. So the width, again, we'll line up our ruler, the edge of the container, and it looks like this one is how many lines past the halfway point? 1, 2, 3. I'll call it 10.80. And there's no real way to know if you're estimating perfectly. Just do your best job. So again, now we're doing the 3rd dimension. And here you can see it lines up at about 5.1, and you can see the edge of the box is not quite at 5.2, but it's more than 5.1. So I might say 5.18, and that's my guess. You may look at it and see something different. So now using these results, you're going to be calculating the volume. And the formula will be length times width times height. So you're going to multiply your 3 numbers by each other. Your final answer should have the same number of significant figures as the number with the fewest. So here we have 4, 4, and 3. So your answer will have 3 significant figures. And your units, if we multiply centimeters by one another 3 times, will be cubic centimeters. So choose your object, and you'll be doing that measurement and reporting on your data sheet and submitting that online. You only have to choose one object, whether it be a rectangular solid or a cylindrical solid, such as a marker or something similar. So that is part 1. Now part 2 of lab number 2 is determining volumes of water in 3 different measuring devices. So you're going to either randomly fill your containers or have someone that is near you fill the containers, not all the way, but somewhere within the measuring range. And you're going to look at each and take your best measurement, estimating to the proper place as described by your instrument. So let's start with the first one. Here is a container that looks like it holds 250 milliliters. It's okay if you can't quite read the numbers here. It holds 250 milliliters. And in order to get a good reading of our volume, we have to come down to eye level with the sample, meaning you can't see that circle. You see one flat plane, and that's really important. And then we go based on the meniscus, which is the lowest line. So here our measuring device, we can tell it's broken up into groups of 25, which means we can really only guess to the nearest tens place. So I'm going to estimate this has about 60 milliliters of water in it. And I'll write that down. And you'll be including this on your data sheet that you submit for your own measuring devices and your own volumes of water. So here's our next container. This holds a maximum of 150. And we have to come down to eye level. This is broken up into groups of 10. And it looks like there's just about 50 milliliters. So I'm going to estimate, because it's broken up into groups of 10, if we carry it out one more place, which is what we do when we're estimating, you can estimate to the nearest ones place. It looks to me that it's right on the dot, so instead of saying 49 or 51, I'm going to say 50 milliliters. So I'll write that down. So this is in container 1, container 2, and our third container we're going to look at here can hold, this one's harder for you to see on the camera, but it can hold up to 300 milliliters. And it's broken up into groups of 50 milliliters. This is 250, 300. And you may not be able to see it clearly, but we have a 200 mark right about there. So being that they're broken up into groups of 50, we can really only guess to the nearest tens place. So I'm going to say, because that water is almost at the 200 line, I'm going to call it 200 milliliters. So we're going to record that on our data sheet. So these are our three measurements. So really important, when you upload your data sheet and your lab, either a video or a picture, I definitely want to see a good picture of your measuring device. So make sure you show me something like this, where I can see the maximum and I can see the increments. That's really important. I can see that this goes by groups of 25, which is different than this one. It goes by groups of tens for most of the way, and then randomly here it jumped up by a larger increment, and then here we went by increments of 50. So make sure you send me a good picture of each of your measuring devices so that I know what you're basing your measurements and your estimations off of. That will be how I grade your papers. And that is part 2 for lab number 2. So we're ready for part 3 of lab number 2, which is finding the density of a food that you can find in your kitchen. And what you're going to be doing is comparing the density that you calculate to a density that's published online. So a well-respected source has claimed a certain density for a food, and you're going to compare what you find to that density and eventually be calculating percent error for your measurement. So you want to be very specific and very careful with your measurements here. So the example that I'm going to do is black-eyed peas, and I know that I can find that on the web resource that I gave you on Blackboard. There's a link under the supplementary videos that you can click on to look up food densities. So you may want to check there and make sure the food is listed online before. Now once you've selected a food that is on the list that I gave you the web resource for, we can start by measuring the mass and the volume, which are the two things that we need to find density. So, being that I'm using a small object, I'm going to use a small cup and hit the 0 button to make sure that this scale is considering there to be nothing in the cup. This cup is just to contain the beans as I measure them. So I'm going to take a small handful and weigh out some of these black-eyed peas. And you can see this scale is only showing me one significant figure. It's telling me 6 grams. So I'm going to write that on my data sheet. I'm going to write 6 grams. It would be great if you could find a scale that gave you more precision than that, but this is what I have, so maybe that's what you'll end up with too. And now that we've noted down the mass of our black-eyed peas, that's 6 grams, you're going to take this very sample and add it to a measuring device with liquid in it. So this technique is called water displacement. And what we're going to do is, we just measured this in our last part of the video. So we determined there's about 50 milliliters of liquid in here. And we're going to watch and see how far the water level rises when we add our black peas to the solution. And that's going to represent the volume of the black peas, the black-eyed peas. So there we go. Let's see what kind of volume change we're able to observe, again at eye level. And it looks like it rose to close to 60. Now, because these are in increments of 10, we can estimate to the nearest ones place. So I'm going to say it looks like about 58 milliliters. That's what I'm going to write down as my final volume. So the volume rose from 50 to 58 milliliters, meaning these black-eyed peas have a volume of 8 milliliters. So I'm going to write down my initial volume, which was 50, and my final volume, which was 58, which means that the black-eyed peas had a volume of 8 milliliters. So we are going to use our mass and our volume to determine the density using the equation density equals mass divided by volume. So essentially we have 6 over 8, and we're going to use that to calculate our density. So we're going to find a number here, and we'll say grams per milliliter, which is also, like we talked about in lab 1, equal to cubic centimeters. So in the end, you're going to be coming up with a density that is in terms of grams per cubic centimeter. And we're going to talk in detail about calculations using all of this data that we've accumulated for parts 1 through 3 in the next video. And I would also like to add in to be sure to repeat this experiment 3 times. I did it once, for example, but make sure that you take 3 separate samples of dry, whatever it is you choose, weigh it, and then put it into water to notice the water displacement and the volume, and then throw this sample out, get a fresh sample, weigh it again, and then find the volume, because you're going to use those 3 pieces of information, those 3 densities, to average together and conclude what the density of that food is. Ultimately, you're going to be comparing whatever density you find to the one that's available online as a theoretical density, and we'll be finding percent error. So make sure you get 3 replicates of your data for whatever food you choose.